Hello, it's Keith here, and this is episode 10 of the ChibiAkumas series of my Z80 programming tutorials, in which we look over parts of the source code of my game and we see how they work. Now, in the last two episodes, we've been looking at the code of the event stream, which is the interpreter of the binary data that makes up the level. Of course, it works in the principle of having a timed event and a set of events at that time, and those events will define new objects, which are effectively enemies, and other things that happen in the level, such as the direction of the scrolling moving, or the power-ups being taken from the player, and so on. So let's have a look at the code and see at the part we're going to look at today. Of course, as I've said, this is part 3. If you've missed parts 1 and 2, I'd suggest you go back and look at them later. But if you've not seen those, then today's lesson should still be interesting to you, and it won't really matter too much if you've seen them in the wrong order. So let's have a look at the source code of the part we're looking at today. And here it is. So each time in the event stream can have multiple events at it, and it can take up to 15. And so the code we're looking at here, load next event, will actually check if there are any more events at the current time. And if there are, it will read them in and branch out to them. If there aren't, then it will end the execution of the event stream. So that's what we're doing here. This is the count. And then here we're using this RST6 command. Now RST6 within the ChibiAkumas game will do a jump to the memory address in IY. And we've set IY to load in a byte from HL and in HL. So we're effectively setting A to the memory address of the next byte in the event stream here, and what we're doing is we're loading the next time of the next event, and then we're updating the pointer to the next event here with HL, and then we are returning here, and then we're continuing processing the next event here. Now when we get to this point, we're actually creating a single object. So what we're doing is we're reading in here the sprite number of the sprite, because the single object command is in the format sprite xy. So first we load in the sprite here, we're using RST6 again here, and then we're loading in the x coordinate straight into D, the y coordinate into C, we're increasing HL here each time, and then finally we're pushing HL here just to back it up, and we're using the add object command, which we will have a look at next. Of course, when this is done, we just return. So here's the add object command. Now this effectively creates all of the enemies and background objects within the game. It's quite complex, and it uses entirely self-modifying code for the parameters that it's going to put into the object array. The object array being effectively all the enemy sprites that make up the level within the game. So the first thing we need to do is decide if we're going to add to the back of the object array or the front. Now, ironically, if we add to the front, we add to the background, and if we add to the back, we add to the foreground. And the reason for this is we draw the list in front to end order. So the objects that are first drawn will be covered up by the objects that are last drawn. So what we do here is we're using self-modifying code to either put an inc HL or a dec HL in here, and we're also going to either start from the end of the object array or 0, the start of the object array here, just depending on what order we're going in. Now when we get to this point, we're ready to actually start processing the object array. So what we're doing here is we are scanning through for an entry that is 0, because if the y coordinate is 0, the object is not in use. Now when we get to here, we are actually able to add an object, and so once we find a slot, we're going to put once we find the slot, we're going to put the object in, and we back up the memory address of the data in the object array. This is used by some of the boss battles. For example, the Scolder is actually made up of 9 objects, and when the enemy is injured, the sprites have to be changed, and this is done by directly injecting new sprite numbers in the object array data. And so this is used to know the memory locations that we need to change in that case. So here we are now writing the y coordinate, which is the first byte in the object array, and then on the spectrum we are aligning it to a 8 pixel boundary. This is to stop the color clash on the spectrum. And then next we're doing the x coordinate here, and once we've done that, we are then loading in the move. Now you can see this is using self-modifying code, so this byte will actually be the move that has been selected for the current object. Then we're doing the sprite. Now the object array is in a slightly tricky format. We've discussed it before, so please go back if you need to see more about it. But essentially we're using 1/2 of a set of bytes. So here is the object array here, and you see rather than going all the way along here, we're actually going all the way down here and then back up here. And the reason for this is we don't need to change the L coordinate at any point when we're working on the same object. So the L number is effectively the object number, and the H is effectively the attribute of the object that we're changing. So that's why we do it like this. So we set 6 here to jump to that second column within the object data here. Now we set the life, which also affects whether the object will hurt the player. Now there's one trick here. It's checking how many players are currently living in the game. What it does is if there's 2 players living in the game, it doubles the difficulty of the object so that the game will be harder with 2 players. This was to try and mimic the arcade games, which often, if there are 2 players, make the game harder. And this is because ChibiAkumas would be easier with 2 players because you've got twice the firepower being shot and also the ability to attack two enemies at once. So it seemed worthwhile trying to make the difficulty harder. But we do have to cap the difficulty out to make sure that it doesn't go back over 0. And also, some of the boss battles use life equals 255 as a special marker for the hit zones and things that have special parameters. So we limit ourselves to 254 as the maximum life here, just to make sure that we aren't accidentally creating a boss object, which did happen during testing quite a few times. So that's a bug fix there. So once we get to this point, we're now ready to actually create the object. So we just load in the life here to HL, and then this time we're decreasing HL because we're moving back up this pattern here. So we've just done the life, and next we're going to do the program. And we do the program here. Program is, of course, special things like background objects have a special program to make them move more slowly, but also the program in most cases is actually the firing pattern. Then we have the sprite size. This is the hit zone effectively of the object. Objects physical sprite size, as in the bitmap data, is separate, but we call it sprite size here just for convenience. It's actually the size from the point of view of what size of the object can hurt the player, what size of the object can the player shoot at. Animators are a more advanced function. These allow for complex movements, fire patterns and sprite changes to an object. We're going to look at those in a later lesson. They were added with episode 2 and they made programming episode 2 much easier than episode 1. And so when we get to here, we're done. And this is just the finishing part of the loop here, which was looking for a valid object to work with. So that's all there really is to it. Now, all through that you've seen various pieces of self-modifying code for changing the actual data we're going to add to the next object. How do we actually set that? Well, the easiest way is to use banks of settings. So we predefine the various enemies that are in the level, and then we use those predefinitions to set all of the settings in one go. And these are settings banks. What we can do is we can save and load settings banks, and there's 2 banks because it's effectively, while each bank could support up to 15 definitions, with episode 2 that turned out to not be enough. Now the first bank is saved within the core memory, but the second bank has to be defined as being part of the level data because the core was too big by that point. And you can see that represented here. Now this is the first bank, which is within the core, but this is the second one, which is why there's a 2 at the end here, and self-modifying code will replace this with the true memory address in the level data, which is where the temporary data is going to be saved. And here's the actual start of the code that will do the job. And so what we're doing here is we're saving the defined address we're going to work with via self-modifying code here. So here we're working out what bank we're going to work with. So the banks are numbered from 0 to 14. If this is set to a 15, then we are actually saving to a bank here. And what happens then is we load in the next byte from the event stream, and that will be the bank number we're saving to. The reason for this being is saving is very rare, so we can spare an extra byte there, but loading is quite common, so we wanted to keep the number of bytes smaller. So if we are saving, we're going to branch out here. Either way, we need to work out the location we're reading in the data from. There are 8 bytes per bank, so we multiply A by 8. We add it to the address of the bank that we're reading from, and then we start reading in our data. Now here's the loading routine. We use RST6, which will read in repeatedly from HL and inc HL. Load A from HL and then inc HL is 2 bytes. RST6 is just 1, so we're effectively saving a single byte here every time, and that is important when you're working on a Z80 system. So although it's slower, it's very important to use your spare bytes on the very, very frequent routines like the code within your sprite routines, and to just save those bytes where you're doing things 1 or 2 times a frame that really aren't going to notice being a little bit slower. So here we're loading in from RST6, and then we're saving to the various locations of self-modifying code that actually create the object. The save version is almost identical, but we're actually reading in from those locations that have been predefined. And the important thing to notice here is, of course, you don't need to use these banks. The definitions that we use in a typical level will work just fine if we then immediately define a sprite with them. For example, here are the definitions that are creating a sprite of the boss here, but we could use these, actually there's just one more there. If we use these and then did a create object command, that would work just fine as well. The banks are just to save memory and also to save hassle for recreating the same object over and over again. There's no necessity to use them. So when we get down here, we've actually finished loading or saving, whatever we were doing. So we just return at this point. Here's the reset power-up command. Now, the ChibiAkumas game, because it's only 8-bit, I was quite limited with the number of power-ups I could have. If I was working on a PC game or an iPhone game or something, I'd have probably had dozens of the things. But you know, memory and complexity-wise, I had to keep it simple. So all I've got is 2 drones, a faster shot and a more powerful shot. And so to keep the game feeling challenging, I take those power-ups away from the player at the start of every full level. Now, the game levels have 2 parts, and as far as the game code is considered, they're both the same thing. So the first mountain level and the Skulder boss battle are 2 levels as the game's concerned, but they're only 1 level as far as the player's concerned. So the reset is manually defined by this reset power-up command. It's not done automatically as part of the loading of a level, because as I say, the Skulder part, which is still in theory part of level 1, is actually technically level 2. So this will just clear off all of the power-ups from the player using this code here. So here we're just taking the power-up away, we're changing the colour of the bullets back, we're taking away the shot power and the shot speed here. So this is effectively just resetting everything back to the way it was. And that's really all we've got to look at today. It's very straightforward, the remaining code we've had to look at today. The real tricky part is, of course, this code that adds the object, but even that is relatively straightforward in that all it does is it looks for a slot to put the data in and then puts the data in the same format as we saw it being read out before. So there we go. So that's really all we've got to look at today. As before, please check out the website, because there is a text description of all of these with the comparative code. There's all of previous episodes showing other parts of the code. We're still going to continue with this. And next, I think we need to have a look at the player code, which handles the actual controls of the player and the shooting of the player and things like that. That's quite interesting, and that's especially interesting if you're into the CPC Plus, because there's a lot of very special code for the CPC Plus version. And there was a lot of challenge with that, because it had to be very small and very powerful, because it had to support 2 players, CPC Plus bytes and Spectrum and MSX, all in the same piece of code. So that was very tricky, and we'll have a look at that. We'll also have a look at the animator code, which I just briefly mentioned there, which is handling complex animations of different patterns over time. So we'll have a look at that as well. Anyway, I hope you've enjoyed today's lesson. Thanks for watching, and goodbye.